Friends, we are going to see today stress distribution due to surface loading in the soil mass. Let's say you have a ground surface and there is a surface load, point load Q, which is acting at the ground surface. We are interested in finding out the magnitude of vertical stress at any point. Say any point we can take it. This is the point P. What is the magnitude of the vertical stress? Sigma V, or we can say sigma Z, because this is the ZZ direction. This is going to be very, very important, because any settlement of a structure or a footing is a function of this vertical stress due to the load coming on to the footing. So, way back in 1885, a formula was given by Boussinesq known as Boussinesq formula for stress distribution. In a soil mass. Due to surface load. So here surface loading has been taken as Q. This is the surface load. Which is acting over the ground surface. So if you want to find out, this becomes the x direction, perpendicular to the board will be y direction, and this becomes the z direction. So perpendicular to this z, let's say the horizontal distance is r. Then how to find out the magnitude of this vertical stress? The vertical stress sigma z is given by the expression as 3 divided by 2 pi into Q by z square into 1 divided by 1 plus r by z whole square raised to power 5 by 2. This is the famous formula given by Boussinesq for computing the vertical stress at any point. For example, let's say this is the ground surface. So let's consider this one. This is the ground surface. Here this is the vertical load which is acting. So this becomes the z direction. So this is the z axis, vertically downward. This becomes the x axis. This becomes the y axis. So this is YY, this is ZZ, this becomes XX, isn't it? So here the point could be anywhere. It could be perpendicular to this So at perpendicular to z axis, the horizontal distance, you can find it out. The point could be here, it could be anywhere inside the ground. This is the ground surface. So you can find out the horizontal distance in any direction, right? The horizontal distance with respect to the z axis. And that horizontal distance from the z axis is given as r. So r is here the horizontal distance of point P where you want to find out the vertical stress from z axis, right? And this z is the vertical distance from the ground level or ground surface. So this expression, famous expression, is being used, and you can also find out here the shear. Shear can be designated by the symbol tau. So tau, and it is acting along the z direction and contained in a plane r z plane. So you can call it tau r z. Tau r z is given as, if you know sigma z, multiply it by r by z. This is the second expression. So Boussinesq equation or Boussinesq expression, Boussinesq formula can be used, number one, for vertical stress. It can be also used for shear stress. Ta. So this is the second one. Vertical stress, you can find it out. And then once you know the vertical stress, as you know, the settlement of a footing can be computed, which is a function of sigma z. Now, for deriving this expression, Boussinesq had certain assumptions. What are those assumptions? Let's look to that. The various assumptions by Boussinesq was that, first thing, the soil mass below the ground surface is homogeneous. It is isotropic. It's also semi infinite. Soil mass extends in all direction. It is semi infinite, and it is isotropic. It's also homogeneous. That was the first assumption. The second assumption you to get that on this point there is no overburden pressure. That means the soil mass is weightless. So it has no weight. Also, he had the third assumptions that it's a elastic continuum. So soil mass is an elastic continuum. Sir, That means stress to strain ratio is going to be constant. So remembering these two formula, you can compute the shear as well as vertical stresses at any point in the ground, and it has got wide applications, as I have already told you. So regarding this stress distribution, we would like to take a problem. So let's take a problem. Let's take a problem like this, or example like this. A point load of 100 kilonewton is acting over the surface as shown in figure. So this becomes Q equal to 100 kilonewton. Calculate sigma Z at R equal to 0 and Z equal to 1 meter, 2 meter and 3 meter. This is the problem. R equal to 0, that means R equal to 0, that means you need to calculate the vertical stress below the point load on, that is on Z axis. That is the meaning of R equal to 0. So for R equal to 0, the point will be somewhere here. So my point P will be on the Z axis. Now, I know here that Z is known to be in meter. I need to calculate at 1 meter, 2 meter and 3 meter. And the formula is also known to be sigma Z equal to 3 divided by 2 pi into Q by Z square into 1 upon 1 plus R by Z whole square to the power pi by 2. So here R by Z you require it. So if you know what is the value of R by Z, R is already given as 0, so R by Z becomes 0. Therefore, if we can write it in another form also, you can write it as Q by Z square multiplied by the Boussinesq coefficient Kb. Kb is called Boussinesq coefficient, right? Where this Kb is given as 3 divided by 2 pi into 1 divided by 1 plus r by z whole square to the power 5 by 2. This is the value of Kb. When r by z is going to be 0, for r equal to 0, r by z equal to 0, therefore Kb becomes 3 divided by 2 pi. So if you calculate the value of Kb for 3 by 2 pi, let's calculate it. 3 divided by 2 into there is 0.4776, we can say 5, 0.4775, 0.4775. So the value of Kb is known to us. There is known. Now there is Q by Z square. There is Q by Z square. Right? So now sigma Z, therefore you need to calculate sigma Z. So sigma Z in kilopascal you can now calculate it. So as Z increases, here it will be Kb times, this is very important, 1A, formula 1A. So use formula 1A. That is Kb. Kb is already known to us. Q by Z square. And Z is 1. So this becomes 1. Q is 100. So if you multiply this by 100, this becomes 47.75. Now Z is 2. So Q by Z square. So it becomes 4. 100 divided by 4. Q is 100. It becomes 25. So 25 multiplied by this gives you 11.93. Then if Z is 3 meter, 3a square becomes 9. 100 divided by 9 into Kb. 100 divided by 9 into Kb equal to 5.30. So what you do, what you see that when R is equal to 0 and Z is increasing now. So at 1 meter it is 47.75 kilopascal. At 2 meter, just below this, let's say this is 1 meter. At 2 meter, the value reduces from 47 to 11.93, and at Z equal to 3 meter, R is 0, it becomes merely 5.30 kilopascal. So as you go down from the ground surface, the vertical stress is going to decrease. That's a very important conclusion which we get it. So as you going down and down, the value is going to be quite less, and practically it becomes 0 at a particular depth. At depth also you can find it out. At what depth it will be 0. So at certain depth, the sigma Z is going to be 0. So what will be that value of Z? That also you can find it out, because Kb is going to be 0.4775, no change for R equal to 0. So if R is going to be 0, then Kb is going to be no change. Kb is given by this expression. So r equal to 0, kb will be 3 by 2 pi, that is 0.477. So at what depth? Here we can calculate it further. At what depth sigma z becomes 0? That also you can find it out. So in this problem, we can see further. This is the first part. The second part of this problem is at what depth this vertical stress sigma z becomes zero, right? So you know sigma z equal to kb multiplied by q by z square. This is expression 1a, right? And kb for r equal to 0 is 0.4775. No change for r equal to 0. Now, so this becomes 0. This is 100 surface load divided by z square, right? So practically you will have to find it out at what depth this becomes equal to 0. So this is a good exercise for all of you. Brainstorming, you can just do it, and as you go down and down, the intensity will keep on decreasing. It becomes almost negligible if you go very deep, and practically it becomes 0. So you can do this exercise, and also you can find it out the third part. The third part could be, say r is now 1 meter, 2 meter, and 3 meter, and the depth is z is for r equal to 1 meter, or let us say r equal to 1 meter only. So at r equal to 1 meter and z equal to 1 meter, or I will make it this problem like this. Third part will be at a z equal to say 2 meter and r equal to 0, then r equal to 1, 2, 3 meter. Calculate sigma z. So this is the third part of this problem. So how will you calculate it? Now you know it, r by z needs to be calculated. So from the given data, you can calculate the value of r is given to you, z is constant, it is 2 meter, no change. So z in meter, no change. At 2 meter depth, so let's say z equal to 2 meter. This is the here at z equal to 2 meter, r equal to 0. What is the vertical pressure? R equal to 1 meter. So r equal to 0, 1 meter, 2 meter, and 3 meter. So r by z you can calculate. Ratio can be calculated. So r by z becomes 0. Here r by z becomes 0.5. Here it becomes 1, and it becomes R by Z equal to 1.5. So what is constant? Z is constant. This is constant. Z is constant. 2 meter. So Z equal to 2 meter, it's a constant. But R is changing. R here 1 meter, 2 meter, 3 meter. So how the value is going to change? That. So you can find out Kb. For R by Z0, Kb you have already found out as 3 by 2 pi. That is 0.4775. Okay. Now for R by Z equal to 0.5. So R by Z equal to 0.5. Find out the value of Kb. So Kb for R by Z equal to 0.5. This becomes 0.5 whole square. That is 0.25. This becomes 1.25. So 1 divided by 1.25, isn't it? 1.25 equal to 0.8. Then power is 2.5. Multiplied by 0.4775. 3 by 2 pi is 0.4775. So for 0.5 meter, the value you can calculate from this expression. 3 by 2 pi is 0.4775 into 1 divided by 1.25. That becomes something like 0.8 raised to power 5 by 2, that is 0.25. You get 0.27. Now R by Z equal to 1. So this becomes 1. So 1 plus 1 equal to 2. Okay. So 1 by 2 equal to 0.5. So 0.5 x to the power y 2.5 is 0.176 multiplied by 0.4775 gives you 0.084. Then similarly you can calculate for this. Let us see. Now the value, finally we want to calculate what? Calculate sigma z. So sigma z in kilopascal you calculate. So sigma z will be Kb into Q by Z square. So Kb is already known to be now, and Q by Z square. What is the value of Z? It is 2 meter constant. So you can find it out that 0.4775 Kb into 100 divided by Z square, that means 2 2 are 4 is 11.93 kilopascal. Now at Z equal to 2 meter and R by Z equal to this, so Kb equal to this. So now Kb is 0.273 multiplied by 100 divided by 4, that is 25, is 6.825 kilopascal. Now Kb is 0.084 multiplied by 100 divided by 4, that is 25 equal to 2.1. 2.1. So if you plot it, the variation very important, you see the at z equal to 2 meter, there is r equal to 0. At r equal to 0, the value is 11.93, almost 12. So somewhere here. As you go away, that is r equal to 1 meter, the value becomes 6.8, almost half. Then when you go to r equal to 2 meter, so r equal to 2 meter, somewhere here is r 0, 1 and 2 meter, the value becomes 2.1. So from 6.8 it becomes 2.1. That means the value is going to be maximum here at r equal to 0. It is 11.93. This is the variation or locus of sigma z, vertical pressure due to the surface load of 100 kilonewton. Where is the maximum value? The maximum value is below the point load. This is the maximum value, 11.93 kilopascal. But as you go away from z-axis, r is going to increase. The value of sigma z is going to decrease exponentially, and it's decreasing very fast. This is what I wanted to cover in Boussinesq equation. In the next slide, we will next video we will do few more problems on this to make the point clear. So this is the vertical pressure distribution over the horizontal plane at any fixed depth. This is the kind of variation. This is very, very important one. So the maximum settlement will be at the below the point load itself. On the axis of loading, the maximum vertical pressure, and hence the settlement is going to be maximum. Thank you very much.